Thanks everyone for watching this video about AudioScope V2 audiovisual attention architectures for calibrated open domain on-screen sound suppression. My name is Efthymios Tzinis, and this is a joint work with Scott Wisdom, Tal Remez, and John Hershey. So for the task of on-screen sound suppression, the goal is to capture any sound which appears on screen. And of course, as you can imagine, it's almost impossible to gather supervised data to train a model on. This is why we propose a novel model named AudioScope V2, which does not require dependence on object detection models, is invariant to the number and the class of sounds, remains robust when training with off-screen only videos, and on top of that is able to capture audiovisual synchrony features as well as calibrate the results of its on-screen classifier. In a nutshell, we start in AudioScope training with a video soundtrack. We randomly mix it with the soundtrack from the dataset, and we train a sound suppression model using a mixture invariant training loss by also obtaining the mixed assignments, which we use as pseudo labels. We compute a video embedding and then one audio embedding for each one of the estimated sources, and we align them through an audiovisual attention module. On top of that, we extract an audiovisual coincidence score when using a classifier on top of this audiovisual alignment module, where we use it as a soft weight in front of each one of the estimated sources in order to form the final on-screen estimate. And we train the overall model using multiple instance loss between the audiovisual coincidence scores and the mixed assignments. We identify and we try to solve the problems of the previous state-of-the-art AudioScope V1 model, which was not able to capture synchrony-based features, and this is why we propose the new audiovisual transformers and more expressive audiovisual attention layers. We also identify the problem of noisy audiovisual coincidence labels, and this is why we try to train the audio separation network and also freeze the image and the audio embedding networks. For the audiovisual attention, we propose novel layers with self-attention and cross-modal attention, as well as a separable variation of each one of those layers that significantly reduces the computation overhead by factorizing the attention across the attention axis, which is performed. On top of that, we are able to calibrate the outputs of our on-screen classifier that you can think of it as a problem, as a trade-off between the SNR on-screen sound reconstruction of the off-screen sound suppression, as we see here. And we can also specify an operating point for our models that also leads to a desired model functionality, but also a more fair model comparison between AudioScope V2 and all the other models. As a result, AudioScope V2, the joint cross-modal attention, as we show here, significantly outperforms the previous state-of-the-art AudioScope for both on-screen sound reconstruction measured in SNR and on-screen sound detection measured in area under the curve. And these results hold for the filtered and the unfiltered and newly proposed dataset that we made available online. On top of that, we are able to obtain almost the same state-of-the-art results by switching over to our separable attention layers, by also being able to scale efficiently with longer videos, as we show here. As a demo, you can hear one example that we aim to reconstruct the on-screen sound of the ducks. Here is the output of AudioScope V1 operating at 1 frame per second. And here on the right, you can see the attention map obtained by this model. AudioScope V2 learns to be able to capture more transient audiovisual features working at a higher frame rate by also making the on-screen sound reconstruction much better. So thank you all for attending this video. Feel free to reach out to us with any more questions.